As Hierarchical said, I will present you today the work Hierarchical Transformation-Discriminating Generative Model for Fished Anomaly Detection. I will start with a brief introduction. So the motivation. As we all know, learning a deep model that can generalize is still a challenge. The generalization property highly depends on the training data that can be described in terms of the factors of variation, for example, color, pose, illumination. Ideally, invariance to the factor of variation can learn directly, given a large enough data set. But as we all know, obtaining such a large data set in most of the cases is infeasible. So we need to inject some inductive bias into the model to help him to generalize. Inductive bias is a set of implicit or explicit assumptions made by the machine learning algorithm to generalize a set of training data. There are different ways to inject inductive bias. 3 ways, particularly: the architectural choice, the training objective, and the input data. Let's consider the first choice of the architectural for inductive bias. For this, I will give an example, the CNN. Following the intuition that local pictures are highly correlated, the CNN are modeling, they have the inductive bias of modeling locality. And when we use convolution, the presentation is most of the time translated when the image is translated. So a simple way to reduce the sensitivity to small transformation and distortion is to reduce the spatial size using pooling, and then we get the translation invariance. The second inductive bias refers to the training objective. So for this, I will give 2 examples. The first example is the self-supervised learning that we will discuss later in our work. The self-supervised learning is the task defines a proxy loss, and the network is forced to learn what we really care about it. So, for example, if we want to learn, if we want that our network will be robust to transformations and will learn this transformation, we need to make sure that the network is aware of these types of transformations. The second is knowledge distillation. That's transferring knowledge from the teacher to the student, where the logics of the teacher are used to train the student. It's like a big model that was trained on enough data, and then you take the weights of the model and you pass it as an initialization as the weights to the student, and you just it's like a fine tuning of a model with a smaller model. The third approach is using the input data. One trivial solution for this is to use augmentation, like translation and scale and resize and rotation and small deformations. So data augmentations exploit prior knowledge about the data and the human perception. So this prior knowledge is talk about that on one hand, the transformation can change the object class. We all know that rotated bird is a bird. And on the other hand, the people have the ability to identify the class even if the image is transformed. So this is another prior knowledge. Another solution is utilizing the internal image statistics captured by its unique patch distribution. Traditionally, generative model like GAN and VAE, they collected a large group of images and then they model their distribution. Instead, the image internal statistics consider the distribution of patches at the image at different scales. Consider patches at different scales enables modeling high-frequency structure, defined details, and also low frequency, the local regions. So in this lecture, we will focus on the third approach, the input data, and the second approach, the self-supervised learning. Okay, so after this introduction of how we can utilize several approaches for data efficient learning, I will present our work that focus on utilizing the image internal statistics and the self-supervised task in order to perform anomaly detection. Okay, anomaly detection is basically the task of detecting unusual samples in the data. In a standard setting, we are given a large collection of images. In this example, the dogs, and we don't see images from the anomalous class, the cats. In this work, we considered a featured setting where we have only 10 images of the normal class, or even 5 images of the normal class, and in the worst case, only 1 image of the normal class. Our study is motivated by the scarcity of samples in many visual domains, and also in the human ability to solve this task, given a small number of images. So what is the key idea of the work? Our model relies on 2 main components. First component is the hierarchical generative model, which captures the multi-scale patch distribution of image or 1 image or few images. As we have a limited number of samples during training, we can significantly enrich the sample space by considering patches at different scales of the image. Modeling patches at different scales enable us detecting anomalies both in global structures and also in local regions. The second component is self-supervised tasks. As I mentioned earlier, classifier trained on proxy tasks as distinguished between transformation can accurately capture novel samples that are similar to the training samples. We utilize such a proxy in our setting. For each generated image, as described in the first component, we transform these images using a predefined set of transformation. And then we are using a classifier that need to distinguish between the patches, between the images, between the real and the fake images, and also between the transformation of these images. Yeah, so in a minute, I will go like step by step in the model, but for each scale, we downsample the image, and then for each scale, we're taking patches at the same size. So for the small image, this patch will be like all the image, and for the high resolution image, will be small patches. And when we take small patches, we are considering like high frequency details, and for small patches, we are for the small image, we consider the global structure of the image.
By anomalous, do you mean like when you consider the patches, the frequency distribution is not like frequency distribution is like distinctive between different patches?
Like you're asking for what is the anomaly? What is anomaly task?
Yeah.
Okay, so anomaly is like one classification class. So if you are training your model on dogs, then your model knows to model the distribution of dogs. And then given a new sample, like a picture of cat, the model should know that the cat is not part of the distribution. Like in the medical domain, you train the model on MRI of people that have cancer, and then you see a new sample that of a healthy man, and you know, okay, this is a healthy man, it's not a cancer, because the cancer is our normal samples. So our method builds this component into a single model, and at the test time, a sample is considered anomalous if many of its patches for all transformation and scales are considering anomalous. So now we'll go step by step in the model. So we begin with the hierarchical generative model that generates random sample of the distribution of the image. For each scale, we model the distribution of images that have the same patch distribution at each scale. Our method employs a patch gun that consists of fully convolutional generator and discriminator with a fixed receptive field. So for each scale, the generator accepts as input the upscaled image from the previous layer and a random Gaussian noise. It connects it together, and then a residual generation is used to add the missing details from the previous layer. To enhance the ability of our model to represent the distribution of images with the same patch distribution, we apply a fit set of M transformation to all the generated images at each scale and the real images. These transformations are chosen such that on one hand, they don't produce samples outside the class of the object, but on the other hand, they enrich the sample space and thus enable us more faithfully capture the distribution. In the third step, we apply a self-supervised task. The discriminator in each scale is asked to distinguish between real and fake images, as well as between the transformations of these images. For each transformed image, the patch discriminator outputs a map of size h times w. H times w is like the size of the image. And then each vector of this map corresponds to each patch in the image. And then each vector is of size m plus 1, because m is the number of transformation, and 1 is the fake class. And it considers the probability of belonging to one of the transformation or the fake class. So if you, for example, look at the second transformation, transformed image, if it was a real image, the discriminator is optimized to classify all of its patches as belonging to class 2, because it's the second transformation. But if it was a generated image, so it should give him the fake class. And then by this way, the discriminator should classify for each transformation the patches that corresponding to the transformation. And in this way, it will be aware of the transformation. So we train the multi-class discriminator and the generator for each scale and for each transformation. And we are classifying the transformed image as real or corresponding to one of the transformations. Our model incorporates the multi-scale patch distribution and the self-supervised type into a single model. And this allows the modeling of the patch distribution together with discriminant capability of modeling the region of this distribution. At test time, we don't use the generator anymore. We cast the problem of anomaly detection as determining if all the patches of all transformations are real. So given a test image, we apply for the image all the set of the transformations. For each transformation, say the second one in this case, and for each patch, we consider the softmax probability of it belonging to the correct class. So if you're looking at the second transformation, we want it to belong to the class 2. So by removing the first element in the vector, the fake class, and applying the softmax, we know the ith element of each vector corresponds probability of belonging to the ith class. Since the discriminator is trained only on normal samples, the highest the score is, the higher the confidence hour that this sample is normal. We then sum this probability for all patches, as you can see here, over all transformations across all scales, which gives us the final anomaly score for the image. In case of multiple images in the training set, we would capture the interclass variability offered by each training sample. So for this, we condition the generator on each training sample. We are doing this by concatenating to each image the index of the image in the index of the image in the training data. So note that the generator in the multi-shot case learns to generate from multiple images distribution, but the discriminator is the same, it's not changed. The only difference is now is learned from a larger set of images, so from richer distribution. So just one word about the training objective. The discriminator is trained to classify all the patches of all the transformation of the real image as I, and all the patches of transformation I of the generated image as fake, the class 0. And the generator is trained to fool the discriminator by optimize by classifying all the patches of transformation I of the generated image as I. It's a minimax like game. So here are the results for the one-shot anomaly detection. We are the blue color. So as you can see, our model outperforms all the baselines for all the data sets. And already for the one-shot, it gives very high results. We should notice that it's really like you train the model on one image of the normal class, and the normal class, the image that is chosen in random. So if the class is like car, the training image could be a car like with a partial occlusions or illuminations, and still it can recognize all the other images in this class. Moving to 5 normal images, the Paris data set here, this one gives the most improvement, as variability captured by these images is the highest. And as we add more and more samples, we can see a further and further improvement. Here are a few qualitative results for the Paris dataset on the one-shot setting. So given a training image here in the right, we can see 2 generated images, which capture the appearance and the texture of the class, but alter the structure sometimes. And from the true positives, we observe that the model correctly classifies non-trivial images different from the training image in color, in orientation, and zoom. This is a true negative. And the false positive, you can see here the false positive is very similar to the training sample, so it makes sense that the model will make mistakes. And the false negative that are really different and hard to understand. Also by a human, what is the class here? So for the last part, I want to show you one application of our model. It's called defect localization, which is a localized variant of anomaly detection. In this variant, the normal samples are very similar to each other, and the anomalous samples contain subtle local changes. So if you see here the training image, it's not in the right, and the small image is an anomalous image that have a little defect here that is localized. Since our model is trained to model the multi-scale patch distribution, it can easily extend to localized areas where anomalies occur. Here are more examples. So as can you see here, the anomaly score is very similar to the one in anomaly detection, except that in this case, since the image, the anomalous image and the normal images are very similar to each other, and for anomalous samples, only a small number of patches are considered anomalous, we don't need to count for all the patches, because most of the patches will be from the normal class. So the only change is that we don't sum over all patches, but only on 5% patches that receive the lowest score. And we assume that these patches that receive the lowest score, this is a patch that represents the anomalous area. And here you can see the localization produced by our method. As shown in the figure, our approach detects multiple defects of different scales. So if you want to understand how to visualize these local defects, the visualization map is defined here, where this part is H times W map, that H times W is the size of the original image, and it's indicating how real the patches are. So basically, each patch or each element in this map contains the anomaly score of the patch, but it contains the anomaly score of the patches that are only described as anomalous. So the 5%. So if the patch is not considering anomalous, we put a 0 in the element, and for the rest, we put in the element the anomaly score. So we sum these scores for all the transformations, and here is the result. So you can see here, if you look closely, that there are patches. There is like a patches of different sizes, but for all the places that the transformation gives a high score, we can see in a more light white. So we compare our model to multiple baseline on a defect detection dataset called Defect, and our model is on light blue and dark blue. So one half a year format of our work was a model called Different, and it also published about the defect localization. So because defect localization is a task that you don't need much samples because most of the samples are the same. It's like naturally it's a few shots. So they published their paper about few shot defect detection, and they applied several transformations. In order to compare to them, we had another variant. This is the bright blue, that we applied the same set of transformation that they applied to fair comparison. And they are in the brown. So we also made an ablation study to basically compare and to assess the importance of each component in our model. So our model relies on three main components: the pyramid, the transformations, and the generative model. So as you can see here, if we remove each part in our model, we get lower performance. And I think that the thing that influenced the most is the pyramid. So if you use just one scale, I mean without the multi-scale patch distribution, we consider just scale at the same size, the performance is the worst. So this is it. Anyone have questions?